Right. The next thing we need to mention here is on the saturated tables, you have these subscripts, right? You have these subscripts. You have a subscript of F, which refers to saturated, I'm going to abbreviate there, saturated liquid, right? And then G tells us that that is saturated vapor. And I honestly don't know why it's F and G. I think it's from a German translation or set of German words. That's what sticks out in my mind. I've never verified that. And so if we go look at the property tables real quick here, right? So I've got one of these scanned. Notice, and it's kind of small, I know, but you can see here for the saturated liquid, there's a little tiny F subscript and there's a G for the saturated vapor. And we see that on all these others. For the saturated liquid values and saturated vapor values, there's F and G values. Notice for some of these properties, we have this evaporation value, the FG value. Evaporation's okay to call it. I'm just going to call it the difference. The FG value, I just call it the difference. And it's the amount that occurs to go from vapor to liquid because what it is it's if I have UG, for example, the value of U at saturated vapor, and I subtract from it the value of saturated liquid for U at saturated liquid, then I'm going to get the UFG value, right? And so if you went back to those property tables and you took the UF value, or I'm sorry, the UG value and subtracted the UF value, um, the difference between the two would give you the FG value. And that's true for internal energy. It's true for enthalpy. That's true for entropy. So with that in mind, this, this is my F value, and this is my G value. So at a given pressure or temperature, I can go look up in the tables, right? So at a given pressure, for example, I could go say, all right, well, the V value for saturated liquid, the left side of the curve is 0.01659, and the right-hand side of that curve is 38.425. And we could do that for any set of pressures. I could also do it for U's, H's, or S's, right? And so that's why I say pressure or temperature on the y-axis, V, U, H, or S on the x-axis. You draw your curve, you draw your dome, and at whichever you have, pressure or temperature, at that given value, you go look up the liquid and the vapor values, and you compare to see where you are. Are you in the superheated vapor region? Are you large in the vapor? Are you smaller than the liquid value? Right, so let's kind of build on that. Okay, so here's a basic example, very simple example. Write it out here. I'm going to write it kind of large. So we have this recorded. I've got pressure, 20 pounds per square inch absolute. These are my givens, given information. I've got a very specific volume value. I say very specific. It's not very often we have 5 significant figures on something like this. That's too much to measure. It's not practical to measure that much, but hey, they're giving it to us. That's okay. So specific volume, lowercase v, 20.093 cubic feet per pound mass. Okay. And they want us to find, always write down what is it that you're looking for. We want to know the temperature and we want to know the phase. Okay. So we want to know the temperature and the phase. Okay. I know that's kind of small to read, but I think I've got the pressure and the volume big enough that we can keep up with it. All right. So description's coming next. So if you're unsure what your phase is, and you probably will be unsure what your phase is, I would always suggest starting at your saturation tables. Now, why am I saying that? Well, here's the thing. I'm looking for an unknown temperature, which means I'm probably going to go to the property tables because something I didn't write down is the fact that this is water. The fact that it's water. Why is that important? Well, because that's step one. If you go back and look at I told you write this down earlier because we're going to refer to it all the time till you get used to it. First step, what is your substance? In this case, we're working with either water or R134. We'll add more substances as we go. But for now, we're dealing with water. Okay, what do we need to know? Well, I need to know what are my known properties. I need at least two, and they can be anything from PVT, UHS, or if I know the phase, that would also be helpful. And then I need to determine the state, which means I need to determine my phase. Okay, so I've recorded the two properties I know, and that means now I've gone through this. I've got water. I've recorded the properties I know. Now I need to determine the phase. And so that's what we're saying here is if you're unsure what your phase is, and you normally will be, um, go back to your saturation tables and build your chart. That will normally help you. I don't normally have copies of the tables in my PowerPoint. So what you're going to want to do is you're going to want to have your text available, whatever you're planning to use for the test, because you need these property tables for the test. So an older edition of the textbook is beautiful for this. And just go pull those property tables out. The property tables really don't change much from edition to edition. So if you've got a fifth or sixth edition of the text that you bought online for hopefully not much money, those property tables will be just fine for taking the test. Okay, but again, most of the time in my notes, I won't have these property tables. Now, I might, since I'm teaching this online, I might try to do more of that because it does kind of make it easy. But at any rate, what do we know here? So I know I've got a pressure and I know I've got a specific volume. So since I'm not sure my phase, we said just a second ago, if you're not sure your phase, probably start with the saturation tables. We could start at A4, but A4 would have nice round values of temperature over here on the left and random values of pressure that correspond to those temperatures. Here I've got a nice round value of pressure, so I'm going to go to table A5. A5 has a nice round value of pressure. And notice down here, we have a row for 20 psia. So you put your straight edge across there. If remember on your exams, you get to use a sheet of notes, and it's not a bad idea to start making that sheet of notes up as you go. So you can just put your sheet of notes or whatever piece of paper you got laying around, or a ruler. If you want to bring a ruler to the test, I don't mind that. You want to put a straight edge across there. Or you could just write in your book if you really want to, but I'd suggest against that because you're going to have lines everywhere if you do. All right, so you see here we've got given pressure, 20 psi. We've got a specific volume that lines up right here. We have exactly a specific volume of 20.093, and that lines up perfectly with a set of values on our table. So what that means then is that means that this temperature, this corresponding temperature lines up with what we're looking at for here. That is the temperature that I actually want to know. What happens here is as long as you're anywhere from this saturated liquid volume all the way up to the saturated vapor volume, anywhere in between here, this is going to be your temperature at this pressure. The temperature and the pressure stay locked. Remember those flat lines on the PV diagrams. Um, this temperature stays constant until you go beyond this specific volume. So my temperature is going to be 227.92 degrees Fahrenheit. And my phase is going to be saturated vapor. Okay. All right. So I've got additional stuff in here so I could be able to write it on my notes here in class. Temperature is equal to 227.92 degrees Fahrenheit. And the phase would be saturated vapor. Okay. All right. Let's look at the next one. Well, actually, so a little bit of theory here before we move on. We've kind of mentioned this a little bit. Given a pressure or temperature, if you've got a specific volume that is greater than that value for saturated vapor, that puts you in the superheated vapor region, right? Greater than VG, you're in the superheated vapor. And if you get a specific volume that is less than the value for saturated liquid, that puts you over in the compressed liquid region of the PV or TV diagram. All right, and so we'll have a different set of rules we'll talk about at the end here about what do we do with a compressed liquid, right? So there's actually a very simple thing we can do with compressed liquids, but let's focus on vapors and mixtures first. Okay, so here's another example, very similar, but slight change, right? Slight change on this one. Another example. Again, we've got water. So write my givens down, write it large so we can see it in the little camera there. We've got water. I've got, again, a pressure of 20 pounds per square inch absolute, PSIA, pounds force per inch squared absolute. And then I've got a very specific volume again, that is 22.98 cubic feet per pound mass. And I, once again, want to find the temperature and the phase. I want to be able to describe the phase. Okay. So once again, I won't always have the copy of these charts. And I won't always have if I'm teaching in class, I try to write this all the way on the left-hand side of the board and keep pointing back to it. We know our substance is water. I've got a pressure and a specific volume value. I need to determine the phase. I need to determine the phase. So what is my phase? Well, we got to figure that out. And then once I know the phase, I'm going to record the values that I'm after, which are temperature and the phase. Okay. Well, I know I've got the specific volume and I've got a pressure of 20 psi. So again, you can put your straight edge across the table here, 20 psi. And notice that my specific volume that I have is 22.98, and this is the specific volume that is for saturated vapor, and I've exceeded that. So I've exceeded saturated vapor. That puts me over in the superheated vapor region. That means I need to go to the superheated vapor tables. So I go to the superheated vapor tables and I look for the block that has 20 psi in it. Found it. There's a block for 20 psia. And then I'm looking now for a specific volume, again, of 22.98. So I'm going to come down here and go down to the different specific volumes and notice I've got a match. So I put my straight edge across here, right? So that tells me then this temperature matches up with this specific volume, and that's where I'm at. That tells me my state. And so if I need any of these other properties to solve maybe a first law problem, I need a U value, a second law problem, I need the S value, maybe I need both of them. I could, step 4 is record desired properties. I would record the additional stuff that I need. For us, all I need to know is that that temperature is that volume, this volume pressure combination corresponds to 320 degrees Fahrenheit in the superheated vapor tables. Right? So T is 320 degrees Fahrenheit. Always write your units or you will always be wrong. I'm not kidding when I tell you units kill people in our line of work. They definitely crash things. This is superheated vapor. Right? So if there's numbers, if there's units associated with those numbers, always write those units. Okay, now what I like to do is draw this out on a PV diagram so we can kind of see a better idea of what's actually going on. Most of us probably learn a little bit better with a visual representation, so let's draw that. Let's put V out here. Let's put P. I'm going to put the dome kind of over here to the left, right? And if we go back and look, so again, what do I know? I know, and by the way, you don't have to draw these to scale when you draw them. You can see all I've done is just drawn two axes and a little hump. And that's all I need to know because what I'm trying to figure out is at my F value and what is my F value and what is my G value? What is my F and G values at 20 psi A? And we can go, I'm going to finish this out. This video is going to go a little bit long, and that's okay. Um, so at 20 psi A, the saturated liquid value is 01683. 01683. 01683. And I think that is point 0. So it's point, so 0.0, no, quit that. 0.01683. And then the saturated vapor value we found earlier was 20.093. And again, units, these are all cubic feet per pound mass. So for the first problem, we found ourselves right here. And then the second problem that we just did here, we've got a specific volume value out here at 22.98 cubic feet per pound mass. So for the second problem, we were out here, which puts us out here in the superheated vapor region. That's to the right of the dome. Now, if you wanted to add lines of constant temperature in here, that's not too hard to do. We could go, because those are going to come down kind of like this, where I've got a line of constant temperature. This would be T is equal to, we found earlier, this temperature was 227.92 degrees Fahrenheit. And then this one, let's make him a different color. Make him green, maybe. Sorry for those of you that don't see green and yellow too well. All right, so this would be T is equal to 320 degrees Fahrenheit, right? And we might want to know what the corresponding saturated pressure is up there. So if we do that, that's not hard to do. Let me pull my, I didn't have this scanned in, but let me pull this out of my tables real quick here. Right, so this is going to be table A4. So notice it's way down here. I don't know. You can go look in your tables. I'll stop share. So this is 320, and the pressure at 320 degrees Fahrenheit for saturated water is 89.667 psi. So 89.667 psi is what we're going to put on that chart then. So share my screen back here and bring PowerPoint back. That is 89.667 psia. That is the corresponding pressure for this temperature of 320 degrees Fahrenheit. So you can see it's not a pretty graph. It doesn't have to be. It just needs to get your point across. For the first one, we were right here on the saturated vapor dome. The second one, we're out here in the superheated vapor region. You could, if you wanted to, you could draw a line of constant temperature coming across here at 320 degrees Fahrenheit. Okay. Hopefully that helps. Seeing it visually sometimes kind of helps. That's a nice enough stopping place. I always, whenever students are trying to figure out how to use the property tables, one of the first things I'll say is, okay, well, where are your, show me your diagrams. And you can see they don't have to be pretty. They just try to figure out where your phase is. What is your phase right now? That's going to be important as you move forward. All right, I'm going to stop here.